Hi there, this is Ryan Malloy here at the Worldwide Center of Mathematics. In this video, we're going to discuss how to determine if a given graph could possibly be the graph of a polynomial. Here we have three different graphs, our red curve, yellow curve, and a green curve. And we have four different equations. Y equals x to the fifth minus 13x to the third plus 7. Equation B is y equals negative 5x to the fourth plus 6x. Equation C, y equals 5x plus 3. And equation D, y equals x to the sixth over 10 minus x squared. And we haven't plotted any specific points on these graphs, but the general shape should be enough to determine if they could possibly be the graphs of any of these. So we'll start one at a time. Equation A. Which one of these graphs could possibly belong to equation A? Well, there's an important characteristic of these graphs to take into account, and that's the end behavior. We notice that with our red curve, as we move towards negative infinity, the curve moves towards negative infinity. And as we move towards positive infinity along the x-axis, the curve shoots up to positive infinity, as indicated by these arrows. Yellow curve, on the other hand, in both directions, the curve shoots up to positive infinity. And the green curve, as you move towards either infinity, the curve shoots down to negative infinity. So how can we use that information to match up with these equations? The answer lies in the exponent of the first term. If the highest exponent is odd, then the graph of the curve will go into opposite directions as you move to positive and negative infinity. But if the highest exponent in the polynomial is even, then the graph of the curve will go to the same direction as you move to positive or negative infinity. So we know that this curve must belong to a polynomial that has an odd power for its highest exponent, whereas these two must belong to polynomials that have an even power for the highest exponent. So we know right off the bat that if we're trying to find the graph that belongs to this, it can't be the yellow or the green curve, because those have the characteristics of an even exponent. But we see that our highest exponent here is 5. So it would appear that this matches up with A. Circle that for now. The only other equation that we have here that starts off with an odd exponent is this one, equation C. But equation C is linear, and clearly none of these graphs are linear. So we can determine right off the bat that C is not graphed here. Okay, so that leaves B and D, both of which have even-powered highest terms. So how do we figure out which one is which? The answer lies in the leading coefficient. We see here that the leading coefficient is negative. And for equation D, the leading coefficient, although it's a fraction, is positive. For functions whose highest term is in even power, if the leading coefficient is negative, then its behavior will look like this. And that as you move to positive or negative infinity, the graph of the curve will shoot to negative infinity. So it would appear as though this belongs to B. And the opposite is true when the leading coefficient is positive. That should indicate that as you move towards positive or negative infinity, the graph will shoot up to positive infinity. So this appears to be here. Now, one other piece of information that we have that we can use to verify that these might be the correct graphs is looking at the y-intercept. Here, for this red curve, we see that the y-intercept is clearly greater than 0, which means if we plug in 0 to equation A, we should get a y value that is greater than 0. We see we plug in 0 here, and we're left with y equals 7, which appears to match up with this. However, you notice that both b and d don't have constant terms at the end. So if you plug in x equals 0, you will get y equals 0 for both of them. And that appears to match up with what we have here. We have a point at 0, 0, and a point at 0, 0. So it would appear as though these are the correct graphs for these three equations. And equation C, sadly, does not have a graph on the board. My name is Ryan Malloy. We've just discussed how to determine if a graph could possibly be the graph of a polynomial.